Hello ladies and gentlemen, thank you for joining me again. This is the fourth lecture for GGS300, Introduction to Quantitative Methods for Geographical Analysis. Today I'm going to be focusing on spatial descriptive statistics, but just before I begin I have a couple of announcements. So thank you very much for all of you who handed in your assignments last week. They've now been marked and the marks will be released in due course. To anyone who didn't manage to get it in on time or hasn't submitted the work yet, please do ensure that you submit that. Everything that we do this term will be cumulative, and therefore it's really important that you do that work and you understand that content, you cement that knowledge, so that then we're able to move on to more complex concepts and methods later in the term. So today I'm going to be setting the third homework assignment for you all. Let me know if you have any queries with that work or any queries with any of the previous assignments which have been set. I've definitely been getting some good feedback from those of you that I have engaged with, so thank you very much for that information. And I definitely welcome many of you to let me know your thoughts if you do have any, particularly given the fact that we do have a long semester and I definitely do have time to ensure that the course material is definitely hitting the notes that you guys are interested in, and there is still time for me to add in content which may be particularly pertinent to your own interests. Okay, we will be having some tests that come up soon, and these will essentially be tests which draw to a close this part of the semester, which is focused very much on descriptive statistics. So I would say generally it's the easier part of the semester before we move on to inferential statistics, where some of the concepts start to get a little bit harder. So watch out for the announcements that are going to come soon on this. And I'm also going to start the discussion board this week, and watch out for an update on the course outline, because I think I probably will start adding in marks in order to encourage you guys to actually engage with the discussion board and also some of the tests to make sure that you definitely get the most out of this module. So, as I said, today we're going to be focusing on specifically the spatial elements of descriptive statistics. So last week we went over some of the aspatial aspects of the different measures which are available to describe data sets. And today we're going to be focusing very much on considering the importance of descriptive techniques, but within the spatial science context. And there's a variety of different metrics that we're able to produce, which are specifically designed to help quantify those patterns within spatial data sets. Okay, so what exactly are spatial descriptive statistics? And you will remember these three different areas that we covered previously. So this holy triumvirate of different metrics that allow us to describe data sets. So the central tendency, so individual values which tell you something about the mode of the set of normative data, or the mean or the median of a set of ordinal or other types of numerical data, which allow us to understand how centered certain values are in relation to the center of the distribution. Then, of course, we have the dispersion metrics. So think of this in terms of the standard deviation or the range, the interquartile range. And then finally, we have the measures of shape. So how skewed the distribution is, whether it's skewed to one particular direction or other, the degree to which there's elements of kurtosis in the distribution. So we are going to be interested in these properties, but specifically how they might relate to spatial data sets, which, ultimately that's what this course is about. This is about geographical analysis, so we want to consider spatial data. And this really is just a table taken from the book which summarizes those different aspects that we're really interested in. So specifically those metrics relating to the central tendency and then different types of dispersion, so the absolute dispersion in the unit upon which you measure the data, or the relative dispersion, which gives you some understanding of the degree of dispersion relative to potentially other data sets. So I think one of the things that you'll notice is that we don't necessarily have distributional shape metrics here, and so the degree to which something is skewed, or the degree to which there is a large degree of kurtosis, and that's just because it's not really that relevant for geographic data. You know, we are able to visualize the data when it's spatial like that in some sort of a map, whether that's 2 dimensions, so just on an XY plane, 3 dimensions where maybe we have X, Y, and Z, so we also have the height potentially of a set of spatial data, or 4 dimensions, so essentially where you have the X, Y, and Z coordinates for the 3-dimensional space, plus a 4th dimension of time. So you can visualize that type of data across those different dimensions, and that provides you with a really kind of nuanced understanding of how different processes might take place, for example, whether that's migratory animal movements because you put GPS trackers on them, or whether it's people moving through space and time that you're interested in. So, descriptive spatial statistics, what do we use them for? Well, we're able to conduct studies explicitly analysing spatial data. So let's say we have a set of point patterns or line strings, then we might want to understand the degree to which they're spatially dispersed or clustered in space, as this really helps to provide information about how certain processes take place in space. In order for us to actually carry out these statistics, though, we have to have some key metrics. For example, we must have coordinate data, so that's basically some sort of geographical positioning information, preferably explicit. So here I've stated it as XY coordinate data. And then that X and Y coordinate data is going to have some sort of coordinate reference system attached to it. It helps if you know that CRS, that coordinate reference system, but then if you don't, there's actually ways for you to kind of figure out which CRS the data may be in. And then also you could have more sophisticated types of spatial data. So if you imagine the first, imagine you had a point in space, so one XY coordinate. A line would then be a feature which had 2 points, and you drew the line between it. And then you could have a polygon feature where maybe you have lots of points, maybe 4 or 5 points, and then you draw the lines between each individual points in order to form the boundary shape. And you'll be familiar with these types of boundaries because we've discussed them before, and we've spoken about things like census tracts and state boundaries, for example. And this is how you start to draw dimensional shapes, by using essentially just points. So if you see a polygon shape, it's actually just points underneath, but they've been processed in a way to draw the boundary around them. So anyway, my emphasis here is that you could have individual points or line strings or polygons, which then you could extract data from, or you could process just exactly as they are. So when I say you could extract data from, there's a good example here. If you had polygon data, so imagine you had polygon data for each state, and you had the state boundaries, the centroid point could be the middle point of that shape, which then you extract as a point. And you could process that in some other way, depending on what your research question was and what you wanted to do with it. So geostatistics, so this is just another name for spatial statistics. How do we calculate those stats? I don't use Excel or SPSS very often, but you don't really have the functionality that you need within those types of spreadsheets. I do use Excel actually occasionally to do small calculations to validate that my main computer code is running correctly, but that's really just that's something that you would do you wouldn't do it very often, and you'd only do it to just validate that things are working correctly. So these aren't really the tools that are very useful for doing geostatistical analysis. Next on this list, we have geographic information systems. So obviously, many of you will be familiar with these types of computing software platforms. There's been a huge expanse in GIS analysis over the past 2 decades. One of the industry standard analysis packages is ArcGIS. You do have to pay for that software, so I know lots of people in the department and the faculty like to use it. I personally don't use it because you have to pay, and therefore it's annoying. You need to get the license every time. But I suspect that there's a campus-wide license that you might be able to use, or it will definitely be installed on the computer lab Citrix platform that I know some of you have accessed before. But also I just put down QGIS here, Quantum Geographic Information Systems, because that's the open source equivalent of ArcGIS basically. And QGIS has essentially all the functionality that you would need, and it's free. So that's always a bonus. So GIS is great for doing geographic analysis within a graphical user interface. So it has a set of inbuilt functions. A lot of the things that we have touched on so far, or which we will be touching on in this lecture, and you can click on the different boxes using the mouse to run certain analyses that you're interested in. And then you get into the programming language world, which definitely a step up in terms of complexity. I know it's hard to engage with the command line, writing code on the command line and running it. I know, some of you are doing very well, so that's great at picking apart to do this type of analysis. But definitely this is where the world is moving in terms of geostatistics, large-scale geovisualization, high-performance computing analysis of very large amounts of spatial data. If you think that every cell phone in the world is generating a whole host of data which is geographically located every second of every day, then that starts to become a huge amount of data, but also a serious task in how we actually process it. So R is one option for doing this. It allows you to do some spatial analysis, or quite swiftly non-spatial analysis too. We'll be covering quite a bit of this in the lab today, so we'll be able to pick up on some of that later. What I'm going to do now in this lecture is just give you an overview of the area. We're going to talk about a lot of the concepts involved, and I'm going to give you some examples of how we apply those concepts. It's going to be higher level than what we will do in the lab, where we will actually calculate some of these statistics. Okay, great. Let's move on. So, spatial measures of central tendency. First, we're going to consider the central feature. So essentially, this is where you have a set of geographic features, and as I mentioned before, they could be points or line strings or polygon centroids. And then essentially we're interested in finding the one feature that has the shortest total distance to all of the other features in the data set. So in this case, we're going to keep it simple. So let's just work purely with point data. So you can do this type of analysis with line strings or polygons, but you would have to do some other, you would probably have to reduce it down to a point actually, in order for you to do this type of analysis quickly and efficiently. And yeah, I do that quite regularly. Definitely reduce polygons down to points quite regularly, just because it's more computationally efficient. So how do we calculate the central point? The calculation procedure essentially is that you will need to find the distance between every single feature in the data set to every other feature individually. So you need to create a matrix of values. That's a fancy word for saying a data frame. And then that tells you how far each point is from every other point. And then you're able to sum that distance, and you can either sum the column or the row, because the number that you produce should be identical. But let's just say that we're going to sum the row, and then eventually we'll end up with a total distance and the one with the smallest sum distance is the central feature. And when you read the chapter this week within the textbook which we're following in this course, so it's by McGrew et al., you'll be able to see how that's carried out, and I'll pick up on some of that within this lecture right now. So I did have a request that somebody said they would like to see my dog, and I thought I'd show you a good example of how we calculate the central feature given my dog's GPS movements. So this is George. He's my black Labrador. He's 3 years old, and he's great fun. So every morning what I basically do is I go to the park near to my house, and essentially I let the dog run off the lead with all the other dogs. So you can just see George here is the black one, and they run around like crazy dogs do, and it's a fantastic way to start the day. So what I'd like us to consider is the fact that, you know, as these animals are moving around, they're creating geographic information. So if we were to put a GPS tracker onto each one of these animals, we'll be able to create GPS trajectories, so they're traces through space as to where that individual entity, so it could be a human or in this case a dog, has actually been. And then we're able to analyze it. So that's George. How do we find the central feature in the park? So this is our stylized park, just here with the green box. Here I am, and this is George. And George runs around, as dogs do, chasing the ball, going to see things, sniff other parts of the park. And then we're able to generate this type of data for basically where he's been over a certain period. Now, if I take that data and I say, okay, find me the individual location every 30 seconds and record a point there, and when we have that location, create an XY coordinate out of it, and then let me extract it. So basically, once we get rid of all of that other information, we have a set of points in the park that we're interested in analysing. So this is the 30-second location interval data set. The question, therefore, is, well, which is the central point within here? And what we're going to need to do as a consequence is we need to build the distance matrix. Okay, so we're going to need to calculate the distance between each one of these to every single other point. So I said distance there, and before we get to how we calculate that type of distance, we're going to need to understand how to calculate the distance in space. So I think, you know, before we get to that point, you can probably guess that the central feature is most likely to be one of these around here, because they're kind of central to the data set, and we would need to calculate it explicitly to work out exactly which one is the central feature in this example. So how do we calculate the distance? So the Euclidean distance, or otherwise known as the straight line distance, is defined by the Pythagoras theorem. We know, thanks to Pythagoras' theorem, that in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the two other sides. Okay, so imagine that we wanted to find the distance here between xi and yi, and xj and yj. So we don't know what this distance here is, so c is dij. So what we do is we take the coordinates for point j and point I, and if we subtract using this theorem just here, the xj value for the x coordinate from the xi coordinate, so that's this value here, we get a squared, and then we square it and add it to the xi value minus the xj squared, which gives us b. So this is the b value just here. Then essentially we are able to calculate this value here. So that would be c squared in the top version, But here, as we're actually square rooting this value, what we end up with is the distance between these 2 points, dij, in the original units of measurements. So there we go. That's how we basically calculate, given these 2 different points in space, what the distance is between them by using Pythagoras' theorem. So I think that's fairly simple to understand. I think some of you have covered this previously in the math that you did at high school. If you haven't, then I think there's plenty of materials to understand this. I think the book is actually quite good at understanding it and describing it. And if you do need a hand, then feel free to reach out to me, and I'll be able to help. So we are able to calculate that essentially between different places. There are different types of distance measures that you're able to produce, but they're basically just more complex versions of what we have. So one option is the Manhattan distance. So basically between 2 different points, you're probably going to have to go through a grid system. So that's one way for you to calculate the distance. That is actually a measure which I have used before. So for example, if you're planning fiber optic, or you're planning your cable company and you're planning a cable rollout, and you're operating in a major city, particularly in North America, because all of the cities are laid out on the grid system, then this is quite a handy way for you to estimate how many meters of fiber optic you would need to connect 2 different points, essentially. So that's one measure, and then you also have the network distance. So this, in reality, the network distance, you could think of it as just a more complex way to calculate. You're able to just calculate the distance over a larger area, but just by breaking it down to smaller pieces. So if you use Google Maps in your phone, and you say that you want directions to go to New York to San Francisco, then what it's going to do basically is it's going to it's going to pull the road segments out of the database, which connect those 2 points. And then if you're interested in getting the distance, then basically it's the summation of all of those individual line string connections between those points. So it sounds very complex to work out, but actually it's just a more complicated way of calculating the distance that we've already covered, essentially. So how do you find the distance between 2 different places? So I think once you start to use more complex geographic information system functions, you'll realize that they sound really scary, and then actually when you get down to understanding what they're doing beneath the lid, it's quite a lot of very simple calculations. You just end up having to calculate them over maybe more entities, or you need to do more layers of calculations. But generally, once you have that kind of layer of understanding, it starts to sink in. Okay, so we're not going to get too bogged down with how we calculate some of these other distance measures here. We know how to calculate the straight line distance, and that's going to be fundamental to most of what we do within this course for the spatial measures. So in the book, in the McGrew et al. Book, to find the central point, you are given a set of points like you have here. And essentially you then want to work out exactly which the central feature is. What I'd like you to do is to examine the distance matrix within the book, because that shows you the structure of how you then start to obtain the distances between each of these entities. So to get that, you essentially need, along one axis, you need to label every single cell. So you go from A all the way through B, C, D, E, F, G. And then on the y-axis, you need to also go A down to G. And then you need to take the measurement of A to B, A to C, A to D. And then you repeat that for every single observation until you have a set of complete distances from every point to every other. And that's how you're then able to start to calculate things like the central point. So let's move on. The mean center. So this is essentially the average location of a point data set. So think of it as being analogous to the arithmetic mean. It's the arithmetic mean center of all of those points. And it's, you can think of it as the center of gravity of a set of points. So the gravity model is a good way to understand flows of trade between cities in economic geography. That's a very well-trodden model. So these metaphors of how we understand entities in space in relation to gravitational forces, that's quite common. And it goes back to Tobler's law of geography, in fact. That things that are closer together are essentially more similar than things that are further away. That's why the gravity model fits quite well these spatial processes. Okay, so how do we actually calculate the mean center? Well, we basically need to sum the Cartesian values, so sum all of the x coordinates and sum all of the y coordinates separately, and then we basically divide each one of those units by the number of entities, the number of points within the data set that we have. And that provides us with some understanding of the mean center when we combine the x and the y coordinate together. So let me give you an example. So we'll go back to George in the park running around. Today there's lots of dog walkers in the park, and George is running around going to see everyone basically, and I take those same points. The question is, well, where do we actually find the mean center within all of these different locations? And to do that, we need to actually take those points and get the x bar value. So that's essentially the mean x coordinate, as we show just up here. So that's the summation of all of the xi coordinates divided by n number of coordinates within the data set. And then how do we find the y coordinate, the y bar coordinate? So that's the sum of all the yi coordinates in the data set, again divided by the number of entities that we have. And that provides you with a way to find that central point. There are some advantages and disadvantages of this particular measure though. So for example, you need to keep in mind that whereas the central feature is explicitly within your data set, if you use the mean, so the mean center, it doesn't necessarily mean that it might fall within the area of study that you're actually interested in analysing. So here's a good example for Maryland. Obviously, it's got quite a non-regular shape due to various political boundaries and geographic features. But it does mean that you could end up trying to take the mean center, and it might not necessarily fall within the exact polygon area that you're interested in. This especially happens when you're working with countries with lots of islands. And if you're doing something like I sometimes do, and you're planning where to build new infrastructure assets, your central mean location, which often I use to try and find the best place to put a new asset, could be in the middle of the sea. So it's really important that you check this, and you might have to introduce some control to make sure that you actually find the point that's closest to the mean center on land, for example. And then I think also it's just worth emphasizing that given the fact that it's a mean rather than a median value, it's highly sensitive to outliers. So you will remember when we studied the income distribution in the US, that was highly positively skewed, and that the mean value was significantly overestimating, or the mean value was significantly higher than the median value, for example, because the mean doesn't respect necessarily how many entities there are within the full range and therefore you could end up with a much higher value for income than in reality, obviously, because there's lots of people with lower incomes in that distribution. You have people like Jeff Bezos and Bill Gates who skew the distribution quite far out to one side. So the same sort of issues can happen here. Okay, great. And this is just an example straight out of the book. So it's just calculating the geographic centre of the US population from 1790, so only a few years after the Declaration of Independence, all the way through till 2010. And you can see that the census centre, as a consequence, has been moving in a southwest-west position as settlements essentially have started to move further west over time. So in the previous lecture, we did cover the importance of using weighted mean samples. That's a good way, for example, to help to understand the income distribution if you have a lot of people in certain groups who maybe make a very different amount to some people who make a lot, but you've only got a few people in those categories. Here, you might be interested in calculating the weighted mean centre based on the fact that you have commuters. So it's an inherently spatial problem, and we're interested in finding the weighted mean centre given how many people actually commute to a particular location. And what you'll notice within this particular equation is that we have Fi here, which represents the frequency or the weight of a particular point. So you could have a central city like DC, and then what you might have is a number of commuters who are coming from areas of North Virginia or areas within Maryland, and essentially you would have an understanding of how many commuters there might be in each one of those particular settlements within the DC catchment area, essentially. And you might want to weight a metric of interest, for example, travel time or distance, based on the phenomenon of interest for your research question. Okay, here's one example. So this is taken from the McKinsey Global Institute, and it's examining the Earth's centre of economic gravity essentially over the past 2,000 years. So as we go through the Industrial Revolution, that centre of gravity was moving closer towards Europe, and then after the Second World War, moving much further over the Atlantic Ocean because of the weight of the United States. And now since about 1950, the economic mass has started to move back eastwards again due to the rise of other economies, particularly in this globalized environment upon which we now live. So how do we find the median centre? Well, the median centre essentially is the location that minimizes the sum of the unsquared distances, but it's less easy to calculate than some of the other metrics which we've already considered. So, for example, actually determining the Euclidean median generally means that we have to go through a repetitive process to find the minimum value between the sets of points within the data set. So what that essentially means is we need to iteratively calculate all of these different values to try and find the value with the lowest distance, and then that will end up becoming the median value, for example, because we try to minimize this function here. Thankfully, computers are pretty efficient, so when you do need to calculate these types of metrics, these days it's not too computationally time-consuming to actually calculate. And you can examine the median centre of the US population given the census that's been carried out. Okay, so in the book, it also covers the linear directional mean. So what is this? Well, it's the average direction for a set of lines. So you might want to obtain the overall trend for a set of hurricane paths, for example, the direction that it's most likely to take. And the resulting answer would be the angle of the mean vector. This is quite interesting. I am teaching from the textbook in this module, and I haven't used this measure before, so it was quite interesting to read up about it. I've not done any hurricane modelling or very much geophysical modelling, where often the direction of a fault or the direction of a magnetic field, for example, might be very relevant to your research questions. So I haven't used this before, but I'm definitely interested in this approach. So essentially what you need to feed into the equation here in order to obtain the output is theta I, and theta I is essentially, it represents the direction of a set of linear features, which could be expected paths for a hurricane, or it could be some GPS trajectory information as people move across space at a specific time of day, for example. So the example in the book is focusing on hurricane trajectories, and these are historical. These are historical hurricane paths, and what you're able to do, given this type of information, is then to calculate the mean direction given this historical information. So, spatial measures of dispersion. So this is a very important measure which we will be calculating within the laboratory. So the standard distance. So you can imagine the standard deviation that we calculate in the spatial descriptive statistics lecture. In this particular case, we're interested in the method which is kind of analogous to this, which is the standard distance. So it's able to measure how much absolute dispersion exists in a point data set, and its absolute dispersion, which is therefore dependent upon the values of the mean. So we're able to calculate it in multiple different ways, as we're demonstrating here. You will remember that this calculation is quite similar, or it's very similar to how we calculated it previously. So essentially, what we'd be doing in the sample is finding the sum of squares and then dividing by the number of degrees of freedom, and then taking the square root of that. And here we do something quite similar, except that we're dealing with x and y coordinates, essentially. So here's an example of the standard distance. And so we have a higher standard distance here, where George has been running around because of all of these other dog owners, in comparison with this situation here. Maybe there wasn't anyone else in the park that day, and George was just running much closer to me, and he wasn't interested in what was happening on the horizon. And therefore the dispersion among those sets of data points is much less. Okay, so you'll end up with a smaller standard distance overall. So can you see that here we have much greater dispersion of those points, whereas in this second example, the points are essentially clustered much closer together. So it's the same again. We're able to calculate the weighted standard distance. So again, this would be good for commuting problems, calculating, maybe you want to optimize the mean travel time to a new shopping center. And the question which your client is asking you is, where should I locate my new shopping center? Given the fact, so shopping mall, given the fact that I have these 5 different real estate sites. And then essentially for each of those real estate sites, you might want to take all of the commuting information which you have, and you might want to weight it based on the number of people commuting from each of those distances. And therefore, as a consequence, you would end up with a set of weighted standard distances for where the population lays and has to commute to each one of those locations. The idea being that if it's closer to you, then you're probably more likely to go and shop there. So that's why this type of metric might be of interest. So you can also calculate the standard deviational ellipse. So in order to do this, we essentially take the orientation of the point pattern into account with the standard distance. So we have three different steps that we need to carry out. So we need to calculate the standard distance separately for the x and y coordinates. And then we need to get the cross of dispersion, essentially by taking the SDX, as we calculate it here, and the SDY from the mean centre, parallel to the x and the y axis respectively. And next, then what we do is we rotate based on a trigonomic function to minimise the distance of these points in terms of the cross arms. So just to give you an example of that, here we're able to take the standard deviation, the standard distance, that's what I meant to say, standard distance of the x values, the x coordinates and the y coordinates here. And then what we want to be able to do is actually rotate this in order to obtain the standard deviational ellipse. And that's very theoretical, of course, so what's the example that you're showing me, Ed? Well, essentially, this example is from the book, and the book is examining data. It's the number of piracy incidents on the east coast of Africa. So particularly this area around Somalia is it's very active in terms of the number of pirates that operate in that area. So if you are working on an oil tanker or a major shipping container vessel, you basically have to be very aware of when you're passing through this area, because people can come up to the ship in very fast boats and try to climb aboard the ship and basically rob lots of the contents or basically steal the ship and try to take it somewhere else so they can get the contents. So this is an example of the standard deviational ellipse based on the data for 2009, where it's smaller than the standard deviational ellipse for 2010. So the question is, well, why is that the case? Well, then perhaps the difference between those 2 years is that it's more lucrative, there's more people as a consequence doing this, they're making more money, therefore they're able to actually invest more in technology and able to travel a longer distance essentially in order to try and intercept these ships and steal cargo. So we do have some issues with the relative dispersion. So it's very clear when we use a spatial descriptive stats that the standard deviation is an absolute measure, so it gives you an answer based in the unit upon which we measured the original data. Whereas the coefficient of variation is relative to this, so it's able to help us understand what the percentage of variation is, and that therefore it's useful when we want to compare different data sets. Maybe those other data sets are of different places, or maybe those data sets are measured in different units, and therefore the coefficient of variation in those circumstances is useful. In geostatistics, however, there may not necessarily be a spatial equivalent to this metric. And that's, for example, because when we change the coordinate reference system, the mean centre might change, but the standard distance between the points doesn't. So then if we actually take the standard distance and divide it by the mean centre, it's not necessarily that useful a metric. And I've just given you an example here. So this is from the book, and there are a set of arbitrarily distributed points, and they've been dropped on the first graph and then dropped on the second graph in different places, but the relative difference between the points has stayed the same. So for example, if we look at the mean centre, it ends up providing a different set of coordinates for that mean centre. So here it's 3.81 and 2.51 as the x and y coordinates, or the x and y coordinates. And here we have 6.81 and 3.51 as the x and y coordinates. But when we actually look at the standard distance, you'll see that we've changed the coordinate reference system, but the standard distance between those points has actually stayed the same. Okay, So therefore, that means that we do need to add some additional area or regional boundary in order for us to understand the degree to which there is dispersion among the particular data points of interest. So if we just look here at the cases on the right-hand side here, so this is the first group. They actually have the same standard distance values, but in theory they should actually have different relative dispersions. So you can see that the points are actually the same in each one of these individual boundary areas, but the boundary area has been increasing at each step. So if you're looking at the smaller boundary area here, in terms of that boundary size, the points are actually quite dispersed. But as you increase the boundary size up here, the points are now relatively clustered with this large expanse of space around the outside of them before you get to the boundary. And then this contrasts with this second group, essentially where you have the opposite. So essentially you have similar relative dispersions because they are essentially the same pattern and they're the same kind of density within this boundary area that we created. But it does mean that there will be different standard, different distances because of the way that the boundary has been drawn. So the solution is essentially to obtain the relative distance. This measure is based on a point's pattern's standard distance and the size of the study region. And this issue is something which is perennial in spatial science. When you're trying to deal with a set of points, whether it's population, for example, and you need to capture density issues, or when you're dealing with distance over different sized areas here, and it all comes back down to the spatial modifiable areal boundary problem, which is that we're artificially specifying where boundaries exist, and therefore we need to take these into account. That's why the relative spatial dispersion might be a good option to understand the standard distance in a particular instance. So how do we calculate it? Well, we need to get the denominator. So essentially, we want to take the radius of a circle with the same area as the study region. So you can see down here, the radius A is the denominator, RA. We've already got the standard distance. But essentially what we need to do is we need to solve the radius given the area. So if we know that DC is approximately 68 square miles, we then need to solve this equation pi r squared in order to obtain the radius 4.7 miles. And that then allows us to make a direct comparison of point patterns in differently sized regions, which is a nice thing to do because we don't want these spatial boundary issues or the way that we aggregate or disaggregate our data to have too much of an influence on the output metrics that we want to produce. Okay, so this is the end of the fourth lecture on spatial descriptive statistics. Thank you very much for tuning in today, and I will look forward to engaging with you on the laboratory work, which I will be setting shortly. Do watch out on the Blackboard page for new updates for all of the content that's going to be coming through this week. And thank you very much for tuning in, and I'll look forward to seeing you all soon. Thank you. Goodbye.